Good morning, everyone. I'm Willa, a PhD student at the University of Chicago from Lab. Today I'm presenting TorqueCapsules. I'm holding one of these in my hand. This block is trying to kind of move my hand a little bit. If I let it go, it can flip and jump. What makes this work is inside there is a flywheel. A flywheel is essentially a spinning mass. It can store kinetic energy and convert it to torque. It first spins super fast, and the moment a brake is applied, the spinning is suddenly stopped, and a change in the angular momentum will cause the outer shell to counter-rotate. And what's unique about this actuation is that what actuates the outside frame is actually within the frame. This unique torquing principle has been explored by researchers to enable robotic self-motion, such as self-balancing, self-assembly, and to provide kinesthetic haptic feedback, such as collision, inertia sensation. However, flywheel actuators are very hard to build, interact with, and control. One of the challenges is building one requires complex hardware configuration. You can see from this early prototype of mine, there are lots of wires coming out, and there were lots of questions came into my mind too, like what motor is suitable, what motor driver should I pick, how can I make a flywheel, what type of battery is suitable, all that questions. So it's not easy to build one. And even if someone built one, it's very scary and dangerous. And then when I tested this, I also made a credit case to protect myself from interacting with it. And lastly, their working principle and controls are very unintuitive. And lots of physics education research has reported how unintuitive this mechanics is. So due to all of these factors, although flywheels are very versatile, they are pretty much confined in a very technical user group, not yet widely adopted by a broader audience like makers, artists, designers. So there has to be a toolkit for flywheels. How do we design one? And let's look at a good example. We took inspiration from one of the most commonly used prototyping tools, servo motors. A servo motor nicely packages many subcomponents and has a horn that allows users to interface to do their custom applications. And similarly, we introduced a hardware architecture of TorqueCapsules, which packages all the subcomponents inside a fully encapsulated shell. It can also be quickly customized for different applications by swapping lids, just like the horn on the servo motor. So in this work, we propose TorqueCapsules, a platform to empower flywheel-based interaction design. It contains a motorized spinning mass and maximizes the torque generation using an electric brake. It contains all the components inside, including a flywheel motor set, a voltage converter, a microcontroller, motor driver, and a 3.7 LiPo battery. And on the back, we have a port for users to upload code. The customization lies in interchangeable flywheels and lids. For example, the original lids can be easily swapped to a belt lid to make it a wearable. A lid can be designed to be Lego compatible and can also allow handheld applications very easily. There are many parameters involved to control this momentum-based actuation, and we also developed a custom GUI to help users with understanding and control. So in our GUI, the user can add two primary commands, speed and brake. User can adjust the motor duty cycle and direction, and adjust the duration of spinning. We can also control multiple motors. And the spike in the red block that you notice is actually part of a torque graph, meaning that the torque spikes during brake. And when it's placed, these commands will be executed from the timeline. column visualizes the motor spin direction and the torque direction, which aren't always consistent to help user understand. The TorqueCapsule hardware and software allow us to harness the interaction potential of values, and we summarize them into a design space. So as you can see, as you saw, it can flip and jump, and spin and self-balance. When it combines with other materials, it can swing, it can deform them and strike. And besides robotic applications, it can also provide kinesthetic haptic feedbacks such as impact and resistance. And finally, the onboard IMU allows closed-loop angle control where the torque can be angle dependent as the user rotates it. We summarize this design space diagram in our paper, so if you're interested, you can take a look. And going beyond single modules, you can also combine multiple modules together along the same or different axes. This would allow torque augmentation, like doubling the torque, reduce delay by scheduling the brakes, and also multi-axis actuation that goes beyond this left and right motion. So with this broad range of capabilities, what can TorqueCapsules actually do? Let's show some everyday objects being actuated. It can be attached to the back of a mobile phone. To allow self-switch or phone orientation. It can also be attached to the lid of a jar to function as a DIY accessibility tool. And it just screws open the coffee jar. It can turn passive mechanisms and materials into active ones by also simply attaching. So here on the left is a complicated gear train. And we'll attach two modules to the back. That turns this passive gears into an active one. And also the soft material can unroll itself with the capsules attached inside to unroll for users to have lunch. So next we show a versatile haptic controller using just one module to simulate hammering effect, pistol shooting, and also resistance of motion of a fan. And lastly, it can be made into expressive toys and sculptures, such as a self-balancing toy ballerina, a self-spinning globe, and we show a complete scenario of a passive plush toy made into a robot companion. So it swings the back to get attention. It jumps to remind user of a meeting, and it comes to the user. Within a backpack, it can give strong directional haptic feedback to indicate left or right. So since TorqueCapsules is a prototyping tool, we organize workshops with both novices and experts to evaluate how well it supports users, people's hardware prototyping practices. So we recruited a mixture of novices and experts, and each prototype was made within 15 to 20 minutes in a very short period of time. And here are some examples. This user wants to make a super strong ball throwing machine, so he decided to stack 4 modules together and actuate them all at the same time to create super strong torque. And this is a functional yo-yo, a bike simulator with directional haptic feedback, an automated pulley system, a self-swinging plank, and something to prevent you from touching your phone. So to conclude, we present TorqueCapsules, an actuation tool for flywheel-based interaction design. The full encapsulation as an actuator is very unique. It lends itself to a variety of robotic and haptic applications by simply attaching or inserting. And we also organize prototyping workshops with both novices and experts in hardware who find our system extremely easy to use. There is exciting future work to be done. We would like to continue miniaturizing TorqueCapsule by employing smaller motors. And also, one feedback received from the workshop is to develop built-in modular connectors between modules to facilitate combining. And we also like to develop simulation to support design of advanced movements and haptics. We talked about servo motors from earlier, which are pretty accessible and easy that user can just grab and use. And we envision that one day, TorqueCapsules will become part of the maker's toolbox as well and can enrich our everyday environments using actuation. Big shout outs to all my co-authors. They are amazing, especially my second author, Ifan, who is applying for a PhD. We've collaborated multiple times already. All our 3D models and code have been open sourced. So please check our website, and also you can come and try some of our demos after the talk. Now I'm happy to take questions.